Hi, everyone. As he just said, I am Ryan Martin, engineering student at CSU Chico. I am working with Dr. Mohamed Al-Batiti, also assistant professor at CSU Chico, and Dr. Ahmed Al-Romani from SK&A Structural Engineering. And the focus of our research is deterioration detection in prestressed concrete railroad ties using simulated vibrations. So a little overview of what I'm going to be covering. Little introduction, background into the problem. Our proposed field of research are modeling methods, assumptions, preliminary data collection, and analysis of that, as well as the next steps of our research. So in the US, we have over 140,000 total route miles of railroad, in which is contained over 25 million individual concrete ties. Most of this rail network is outdoors, meaning it is exposed to the elements and therefore subject to constant deterioration. Since the rail is a critical element of our infrastructure, it's important to inspect the health of these ties over the duration of their life to prevent deterioration from affecting the infrastructure itself. Current inspection methods in place, including rail defect detection, longitudinal rail stress measurement, track gauge winding strengths, and the others listed below, they have the potential to be time-intensive, cost-intensive, can require an individual to travel on-site to inspect rails themselves, and even can require removal of ties from the ballast. So there are better methods possible. In terms of what we are inspecting for, a few typical failure modes of concrete ties include center negative ties, which is what's shown in the image here as a result of the forces imparted on the tie from the rails themselves and the reaction of the ballast on the center of the tie. Another type that is caused by the pre-stressing steel used to prevent center negative ties is splitting bursting cracks from the pre-stressing forces inside the ties. Another type is rail seat cracks. This is damage caused by the forces imparted on the tie directly at the interface between the rails and the ties. So our proposed research is based on the idea that changes in vibrational frequencies that can be detected in a tie can indicate changes in tie geometry as a result of deterioration. So our testing model intends to analyze the effect of crack location, dimensions, and orientation on the detectable change in frequency response due to an excitation. We constructed our analysis using finite element modeling in ANSYS, defining materials from a paper which we will discuss a little more in detail in a second. Applied a pre-stressing state using the shown here array of pre-stressing steel wires, and then utilized a static modal and transient analysis to try to discover what is detectable in terms of vibration change with the cracks that we are inducing in the tie. So as far as load patterns and crack patterns, as shown in the top figure there, we are concerned in this research with longitudinal, which would be typical of a splitting bursting crack, the horizontal in red in the center, which is typical of a center negative, and then the vertical cracks in green, which would also be typical of a splitting bursting failure. The excitation load is applied over a area of the tie model, which is intended to be a simplified version of the interface between the rails and the ties. And we are examining this in terms of a single rail seat excitation as well as a symmetrical dual rail seat excitation. Some assumptions we made. For now, we're using a simple half sine wave impulse to excite the tie and then record the resulting transient analysis. The ultimate goal of this research is to analyze the response given a random frequency vibration from the field. But for now, we are still using just a simple half sine wave excitation. The material parameters from literature are from a Department of Transportation paper that outlines material properties that are ideal for using with FEA software for concrete railroad ties. In terms of the boundary conditions for the ballast, it is fixed support on the sides and the bottom, and then the tie is given a frictional contact surface with the ballast itself. For the pre-stressing application, the steel wire is pre-tensioned to about 190 KSI, which is typical of real-world tie pre-stressing. This was achieved using the known deformation needed to cause that much pre-stressing in the wires, and then using the coefficient of thermal expansion to cause that much deformation in the wires themselves. Excitation load is a force of about 4.5 pounds. That is a distributed load over the simplified rail contact areas. Just to highlight a few of the key material properties we've used from the Department of Transportation paper in question, the finite element modeling of pretest concrete cross ties with ballast and subgrade support. Primarily, it's driven by our modulus of elasticity, our Poisson's ratio, the tensile yield and compressive yield strength and ultimate strength of the tie concrete and pre-stressing steel. And then we've utilized the extended Trucker Prager model, which is a material definition based on a frictional granular material that's driven largely by the modulus of elasticity, Poisson's ratio, and the yield strength of the material. Before we iterated crack damage, we ran a sensitivity analysis to ensure that our sample rate was not affecting our collection of data, as shown in the time domain at the top graph and the frequency domain at the bottom. You can see that while the amplitude is changing, the locations of the actual peaks are virtually identical. So to maximize the amount of data that we could collect in terms of time, we elected to use the 2 kilohertz sampling frequency. So for preliminary results, first discussing the dual pad symmetric impulse. In the frequency domain, we have in black on both the response of an undamaged tie as compared to the frequency responses of induced damage, and this is in terms of a center negative crack shown in the previous slides. A depiction of the same data is shown here as compared to the 170 hertz line that represents the frequency response of an undamaged tie. And then those 2 red pads show the location of our impulse. And then we're collecting this acceleration data to be analyzed from a specific sensing node that is on the further right side of the rail tie. Additionally, we have similar results, but these were collected with a single rail seat impulse as opposed to the symmetrical rail impulse. Similar outcomes. This is still in progress. We have here damage moving towards a single load, towards the sensing node, and damage moving away from the sensing node here. These 2 data sets will be converging as we continue running trials, and we'll be able to compare directly the difference between what side the force is on, what side the sensing node is on, and where the crack is in the tie. So moving forward in this project, the ultimate goal again is to develop a model that can see frequency trends in random vibration data from the field. So that is the next step for us, as well as developing different crack profiles, so the longitudinal and vertical from the end that are typical of splitting bursting cracks, as well as higher resolution iterations, so moving cracks down the length of the tie at smaller intervals around areas of interest. And I'd like to thank the Federal Railroad Administration and the Rural Safety Center, and thank you all for listening.